Namaste and welcome to yet another lecture of linear algebra through geometry. We were looking at 3-dimensional space and we were looking at the various linear transformations which could transform vectors to another vector, different vectors, and in that we looked at transformations like reflection, rotation, shear, and we have even seen the idea of projection from the time that we started looking into 3D. So, we looked at all that and we saw how some of these transformations differ from what we had in the initial idea of 2D, the same thing in 2D. We could figure out that there were a few more things that were different as far as 3D is concerned, and in the hunt for many more things which are different in 3D, we are now going to focus on the idea of determinant in determinant of a 3 by 3 matrix or a determinant of a transformation that we are going to look at, right. So, that is the focus of this lecture. Let us get on to the notion of determinants. So, let us look at determinant of a 3 by 3 matrix. Yeah. So, let us define the matrix A. Let A be this matrix which is A11, A12, A13, A21, A22, A23, A31, A32 and A33, right. So, what we do is we straight away get into the definition of determinant. So, we define the determinant of A as, we define the determinant of A which we call as det of A as A11 into the determinant of this matrix A11, let us say A11 into determinant of this matrix A22, A23, A32, A33 minus A12 determinant of A21, A33, A31, A23 plus A13 into determinant of A21, A32, A31, A32. So, this is how we define the determinant. It is going to be the first term, the first row, first element into the determinant of this submatrix minus the second term which is basically the second row first element into the determinant of this matrix. Then we have plus the third row, the first row third element which is A13 into the determinant of this matrix, right. This is how we are going to define the determinant of the matrix. This is typically what we call as the cofactor expansion of this matrix. So, this is basically the cofactor what would you call this is basically the cofactor expansion. So, determinant of A is nothing but, so let us write this, determinant of the matrix A is nothing but A11 into A22 A33 minus A32 A23 minus A12 into A21 A33 minus A31 A23 plus A13 into A1 A2 A21 A32 minus A21 A32 minus A31 A22. So, this is what we call this as the determinant of A. Now, this is not something new, this is something which we have already seen when we try to look at the volume of the parallelepiped. We exactly had something similar to this. Let us try to unfold this, let us try to rewrite this expression in a different way, where we will get to know the relation between the whatever we see here as this expression for the determinant here is precisely what our volume of the parallelepiped that we studied was. So, let us look at that. So, this is basically, I can write this as A11 A2 A12 A13. I can write this as dot product with, what is the vector that I have? The dot product with A22 A33 minus A32 A23, then we have A31 A23 minus A21 A33, then we have A21 A32 minus A31 A22, right. This is what we have. So, if you look at this clearly, you see that this is the dot product of two vectors, where the first vector I am going to call this first vector as the A1 vector, which is basically given by A11 A12 A13, and the next one that I am going to have is basically this looks like the this looks like the cross product of two vectors. So, what we have, this is going to be, if suppose if I call this the okay, let me rewrite this. Suppose if I call this as the vector, if I call this as the vector A, this corresponds to the vectors, the cross product of the two vectors B cross C. This is what we had already seen when we looked at solving that system of two equations with three unknowns. We said that homogeneous system of two equations with three unknowns, we said that the solution to that is basically the cross product of the two vectors. That is precisely what we see here. So, this is nothing but A dot B cross C. Therefore, what we are going to say is the determinant of the matrix A is given by is basically the volume of the parallelepiped with sides along the three row vectors of A. Right. So, that is going to be the volume of the parallelepiped. So, what we are going to say is we have determinant of A is nothing but A dot B cross C, where A is the first row, A11 A12 A13, this is basically the transpose of this vector. So, this let me take this A11 A12 A13, the vector B is going to be A21 A22 A23, and the vector C is going to be A31 A32 A33, right. This is what we are going to have. So, this is basically the volume of the parallelepiped. So, how are we going to have that? We are going to look at it this way. Suppose I have my E1, E2, E3 axis. So, I have this E1, E2 and E3 axis. Let us say this is going to be the A vector, let us say that is going to be the B vector, and let us say this is going to be my C vector. Now, we see that we can actually form a parallelepiped here. You can take it this way and you can complete this. Then similarly, you can complete this guy also. So, this is going to be same parallel to this guy, and you can this is also going to be C, and this is also going to be the C vector. Now, you can see that this is going to be my A vector, and that is also going to be my A vector, and this is my B vector, and this is my B vector. So, the volume of the parallelepiped is basically given by that, right. Now, let us look at what happens if we swap the rows, if we change the rows, if something, I mean, how does the determinant change, right. So, that is what we are going to look at. So, let us look at some properties of the determinants. Some properties of the determinant of a matrix. Right? Okay. The first thing we will do is the following. The first property is, we know that A dot B cross C is the same as B dot C cross A is the same as C dot A cross B, right. We know this, and since we know that the cross product is not symmetric, that means A cross B is equal to minus B cross A, we have certain properties following that. So, since we know we will say we know that A cross B is equal to minus B cross A. This also we proved in the previous lectures. So, as we following all these things, we are going to have a set of properties for the determinant. So, we are going to look at all that. So, what is that? 2. This says if two rows are interchanged, if two rows of a matrix are interchanged, now what does that mean? Suppose I have a matrix A which was actually this, we had A1, A2, A3, B1, B2, B3, C1, C2, C3, right. We have this. Suppose if I change, that means from here I change, so changing rows, I get this matrix A prime, which is basically let us say B1, B2, B3, A1, A2, A3, C1, C2, C3, then the determinant of A prime. What is the determinant of A prime? It is B dot A cross C which is nothing but B dot, there is a minus sign that comes out, minus of C cross A, which is nothing but minus of B dot C cross A. And what is B dot C cross A? That is basically the determinant of A. So, we are going to get this is equal to minus determinant of A. Is that okay? And similarly, we can actually look at the other one. You can actually change the other row, and you can always check that this is going to be when you change the rows, the determinant value is going to change the sign. That is what we have. That is one property of the determinant we have, right? Okay. Let us look at some more properties. The third one. The determinant of the matrix A transpose and A are the same. So, what are we going to do? We are going to say that the determinant of A transpose, let me write this, we are going to say the determinant of A transpose is equal to determinant of A, right. Okay. Now, some more properties. So, we have already said that if you change the rows, we end up getting different I mean we get the sign changed version of the determinant. So, the fourth property we are going to have, the third. So, the fourth property is, suppose we multiply a column of a matrix by say some scalar k by a scalar k, that means we have the matrix A, which was let us say A B C, A1 A2 A3, B1 B2 B3, C1 C2 C3, and I am going to get another matrix, let us say A prime, which is nothing but KA1, KB1, KC1, A2 A3, B2 B3, C2 C3. So, the determinant of A prime, is basically k times the determinant of A. This is something which we can verify. So, we can say that the determinant of A prime is nothing but k A1 into B2 C3 minus C2 B3 minus A2 into k B1 C2 k B1 C3 minus k C1 B3 plus A3 into k B1 C2 minus k C1 B2 k C1 B2. So, we are going to get k out from everywhere. So, I am going to get it as k into A1 into B2 C3 minus C2 B3 minus A2 into B1 C3 minus C1 B1, B1 C3 minus B3 C1, I am sorry, this is B3 C1 plus A3 into B1 C2 minus B2 C1, which is nothing but k times determinant of A. So, what does this mean? Suppose I have, so the determinant of a matrix which is basically given by say some constant times the first column of the matrix, the second column of the matrix, A2. I'll write this as column 1, column 2, column 3. So, k times column 1, column 2 remains the same, column 3 remains the same, is nothing but k times determinant of the matrix A, right. Okay. Suppose if you are going to multiply the entire matrix by a constant C, then we are going to have the fifth property is the determinant of, let us say, k times A. That means every element of the matrix gets multiplied by k. So, I am going to have this to be equal to k cube determinant of A. So, the next point that we are going to look at is, suppose we have this matrix A, suppose let us look at this. We have a matrix A with identical rows. Then the determinant of A is 0. Now, it is easy to see that suppose I have this matrix A whose, let us say, the rows are A1, A2, A3, B1, B2, B3 and C1, C2, C3. Now, assume that if the two rows, the second row and the third row are the same, if the second row and third row are the same, when we look at the determinant as A dot B cross C, we know that determinant is determinant of okay, we will do this the same. Then what happens? The second and third rows are the same, in which case my determinant is basically A dot B cross B, which means B cross B is the 0 vector. So, we get A dot 0 vector and that is going to be 0. Why? B cross B, B and B are in the same direction, therefore, the angle between them is 0. So, you get A dot 0 vector, which is basically going to give me 0, and that is why we say that if the two rows are identical, we say that the determinant is 0. Now, let us also look at the case where the first row and the third row are the same. Let first row and third row be the same, in which case again I am going to have determinant of A, which is nothing but A dot, let me say, B cross A. Now, since the first row and third row are the same, I have used B instead of C, I have used A, the vector A. So, it is going to be A dot B cross A. Remember that B cross A is going to give a vector, let us say a vector u, which is orthogonal to both A and B, orthogonal to both A and B, and therefore, what I am going to get is determinant of A, which is nothing but A dot u. Since A and u are orthogonal, I am going to get determinant to be 0. So, whenever you have two rows of a 3 by 3 matrix to be the same, the determinant is always going to be 0, right. Similarly, if we have the seventh property, if one of the rows of A is all zeros, determinant of A is 0. Now, in fact, we can interpret the sixth property in a slightly different manner. It says if two rows are the same, that means vector wise these two vectors are the same. If these two vectors are same or they are the same direction, you call those vectors to be linearly dependent vector. Therefore, you have two vectors which are linearly dependent. That means the moment you have two linearly dependent vectors, the area of the parallelogram is going to be 0, and this area is what you are going to multiply with the height to get the volume. If the area is 0, naturally the volume will be 0. So, whenever you have linearly dependent vectors, whenever you have rows of a matrix to be the same, 3 by 3 matrix to be the same, or columns of the 3 by 3 matrix to be the same, or multiples of one another, or the columns are linearly dependent, the volume will be 0, which means the determinant is going to be 0 in that case. Okay. The most important property that we are going to look at now is the sum of the sum of determinants is not equal to determinant of the sum. Now, what does that mean? This simply means determinant of A matrix A plus determinant of a matrix B not equal to determinant of A plus B, right. We have one more property. However, the products, if you take, the products will be the same. So, the product of the determinant is equal to determinant of product. Now, what does that mean? We have determinant of A into determinant of B is equal to determinant of the product matrix AB, right. This is what it is. We have also seen one more, we will add one more property. If A is invertible, then determinant of A inverse is equal to 1 by determinant of A. Now, these are all very important properties as far as the determinant is concerned, and in addition to it we have also seen the some of these transformations which basically some of them alter the determinant, like the scaling. We already saw that if you try to scale I mean you try to scale a matrix, the determinant changes, and if you try to scale one particular column or one particular row of the matrix, the determinant again changes. But we found that shearing transformation is not going to change the determinant, rotation is not going to change the determinant, and so on. So, as far as square matrices is concerned, this determinant plays a very crucial role. We have already seen in the case of 2 by 2 matrix, where we employed the idea of determinant to find the inverse of the matrix and to solve a system of equation. So, if the determinant is 0, there is nothing that you can do about it. You say that the matrix is not invertible, therefore, you want to check whether the matrix is consistent or not, whether it will have infinitely many solutions or no solution. That depends on the right hand side vector that you have. So, that is the same, that is what we are going to have here. So, when you try to, the idea of the determinant is basically used when you try to solve the system of equation. The idea of the determinant is also going to give you something interesting about the rank of a matrix. The determinant is also some kind of a scaling factor by which you are going to scale a particular shape, or you are going to scale the volume or the area. So, these are the properties of some of the properties of the determinants. So, if the determinant is 0, you can very clearly say that the matrix is not invertible, because the inverse matrix is basically given by 1 by determinant of A into the adjoint of A, and if determinant is 0, then you are going to get a 1 by 0 problem, and therefore, you say that the matrix is not invertible, right. And when the determinant is 0, we also talk about the homogeneous system of equation. You remember when we did in 2 by 2, we said that when the determinant is 0, the homogeneous system of equation is going to have infinitely many solutions. And so what we are going to do is, in the next module that we are going to look at, in the next module, we will actually be solving system of equations. However, as a continuation from this, we have been looking at various transformations and stuff in terms of scaling, shearing, rotation and stuff. We will ask the same question that we asked in 2 dimension. What is that? The transformations that you see here, they try to reorient the vectors, right. Some of them scale, some of them reorient the vectors. That means the direction of the resulting vector is completely different from the direction of the vector that got transformed. So the question is, for the transformations, do we have fixed directions? That is where we get into the idea of eigenvalues and eigenvectors, and that will form the topic of discussion for the next lecture. Thank you.